Welcome again, second talk of the series. The first time it was about rays and waves. Now today we'll be talking about the geometry behind beam structure and caustics. So again, this is informal, so anybody has any question?
Yeah.
I see most familiar faces, so I don't need to introduce this speaker, I guess. So yeah, so over to you.
Okay, thank you very much again for listening to me. So today I'm gonna use some of the ideas from 2 days ago. What happened? I pushed it accidentally. So I'm gonna continue the discussion about rays and waves in a way. I'm gonna talk more about structured light. Term structured light is catching up as the study of how light fields can be structured for different applications or just for fun, just for understanding fundamentals. Of course, light has always been structured. Now it's just a way to understand the fundamentals behind these shapes that we can give to light in its different degrees of freedom, spatial, polarization, time, frequency. I'm going to focus mostly on spatial degree of freedom. And I'm going to ignore polarization for the most part, even though I will have a couple of slides about polarization, and you'll see why later. And to understand the structure of light, I will think again about rays, just to try to convince you again that rays tell you a lot about the fundamental properties of light. So this is the caustic I was mentioning yesterday, by the way, just to remind you, and we're going to talk about a lot about caustics today. So the type of beams that I will be talking about for the most part are optical beams or optical fields that have the property of propagation invariance of some sort. That is, if you measure them at some plane, they have some intensity distribution, and as they propagate, this intensity distribution stays the same, except maybe for some transformation. So the more typical ones, and at least for this I will use the laser pointer, is a Gaussian beam like this one, right here. So this is more or less a Gaussian. If I let it propagate to the back of the room, it's also a Gaussian. It's a bit bigger. So as it propagates, this beam keeps its shape, but it gets slightly bigger following a hyperbolic expansion. This is the lowest order Gaussian. You can have things that are called Hermite Gaussians, like air Gaussians, and other beams with more complicated shapes. So those are the more simple and natural propagation invariant beams. There are others that seem more mysterious, like the ones that sometimes people call diffractionless or diffraction-free, and as I discussed with Anna, I really don't like that term. There is diffraction, it's just the way diffraction works. And these are beams that have a given profile. As they propagate, they stay the same without expanding. So they seem to be defying diffraction. Of course, if you study things carefully, you see that diffraction is there. And then there are others that are slightly more mysterious, apparently, which do not get bigger. They keep their shape, and they trace a curved trajectory. And this can be like this, so they call accelerating beams, or a term that I don't like so much, self-accelerating beams. They're not doing it themselves, it's the way we build them. So they travel on a curved path like this, or even on a curved path like this, helical. So these are all diffraction effects, wave propagation effects, that you can understand more intuitively when you go to the ray picture. Yes?
So how would you separate these beams from like solitonic solutions?
One word of answer, I think, is terminology. I think so solitonic sometimes
So this would be solitonic solutions?
Yeah, they're solitonic solutions because they keep their shape. So these are on a transverse plane. We use solitons often also to think of nonlinear effects, etc., but not necessarily.
So from that point, like if there is like a typical solitonic dispersion getting cancelled by nonlinear.
Yeah.
So would you call that like not dispersion less, but like cancellation of dispersion?
No, because in this case, I'm just going to talk about linear. Linear. So free space.
Free space.
Yeah. So even in free space, these beams have these properties. And perhaps the best way to introduce this is the airy beam. We were just talking about Michael Berry, so the last visitor here. And so he proposed this solution to the Schrödinger equation that, of course, because the Schrödinger equation is the same as the paraxial wave equation, can be mapped onto an optical beam. And this beam, I'm showing here the intensity. The beam is traveling in that direction. And it decays very quickly in one side. On the other side, it's oscillatory, but it decays slowly. And as it propagates, and here I'm squeezing it a little bit.
Sorry, which one is the Z direction?
Z direction is, I was always told that at school that light travels from left to right. This is a fundamental law of optics. That's why I don't understand microscopy where it goes like this.
Yes.
Yeah. So light is going like this. This is a two-dimensional solution. I'm ignoring Y for now. And light is going like this. And the beam keeps its shape. If you do a slice here, it looks identical to this one. But it travels on a curved path, on a parabolic path. This is a paraxial solution for that. So that seems mysterious. And I think people got a lot of mileage of this apparent mystery. A second mysterious aspect is what is called in a very New Age fashion self-healing, which is if I now come and block a part of this beam, I block this, I disrupt the beam, but the maximum here comes back. So I can go back and forth. You can see that the features heal themselves. They come back alive. So this beam seems to be doing weird things. It self-heals, and it travels on a curved path. And if you solve the wave equation, like the wave solution, you get insights. Like you see that to get the ideal beam, you need infinite power. So that's one giveaway that something is not hyper-realistic. But you can create finite power versions of these beams with a finite aperture. And for a given region, which I made fairly small here, this behavior holds. Let's now think about this in the ray regime. What rays would you associate with this beam? So yesterday we talked about rays and flux lines. The flux lines would follow the same paths as the intensity features. But the rays, what would be the rays that you would associate with this beam? Well, I'll give you the answer. Here they are. These are all straight lines. They're all, and it's a family of rays. And what the intensity feature corresponds to, the main intensity feature is not a ray, it's a caustic. It's an envelope of rays. What is curved is a caustic. Light is traveling on a straight line along each ray, and what we see is an interference pattern that happens to look the same at different distances and be curved. There's no great mystery. So, what about self-healing? If I block this part of the beam, I block some rays. The intensity feature here was not caused by those rays that I blocked. It was caused by some of the rays that were coming from somewhere else. So again, no mystery here. It's transparent what is happening here.
So if the x extent, the minus x, that's infinity.
Here? Yeah. For now, yeah. I can make it finite, for example, like this. And this shows me why I can only sustain this airy-like solution in the finite region. It's the region where I have the interference of two sets of rays causing this fringes. Yes?
In the last day before yesterday, when we had a lecture,
Yeah.
you showed a photo of glass and it showed a caustic. So if we block the rays in that physical interpretation, will the same thing happen?
Yes. So like for example, if I go to my first slide here, I have this caustic. This is no different than an airy beam. with the exception that this is incoherent light, incoherent white light. If I were to illuminate my mug with a laser, essentially what it would have at some segment here is something very similar to an area beam. So they're not so exotic. It's a caustic. It's the most basic caustic in a way. Just a simple parabolic caustic. Caustic has to be curved in 2D. In 3D it can be straight, but in 2D it has to be curved, and the simplest curve is a parabola. So this simplicity is what gives it this nice properties.
So you get caustic with both coherent light and incoherent?
Yeah. So you can think of that or the caustic as a superposition of a bunch of these with different colors that are uncorrelated. The size of the fringes depends on the wavelength. So then you would feel some continuity. If you zoom in, you would see maybe colors around the caustic. Yes?
So you said this is a two-dimensional picture, right?
Yeah.
So what does it mean when you say it's two-dimensional? It extends to infinity in the third dimension? Or?
Yeah, so I can interpret two ways. I can pretend that I live in flatland, that my world is two-dimensional and this is a solution. Or I can assume that, in the third dimension, I just have the same.
It's just the same.
Yeah, so it's a cylindrical solution.
Does this have a three-dimensional analogy?
Yes. And will I talk about it? I will talk briefly about it, yes.
Okay.
So in the Braxial regime, because things are separable, you can do the same. So this in X and this in Y. So you will have a corner that bends in the direction that the corner points to.
So it's a corner.
Yeah, and that has applications. This has been used for extended the depth of focus of systems without knowing that it was area beams. Essentially, this is the Fourier transform of a cubic face, of a pure cubic face. So it's easy to generate. Yes?
Yeah. So caustics are not so, strange, because every time you go from thin lens to a thicker medium,
Yeah.
you would get a caustic.
Yes.
Mostly.
They are everywhere. And that reminds me of something that my PhD advisor said that I found very witty, and I'm going to use an extension of what he said. He was at a party, and the classic thing that a non-physicist comes to talk to you and they want to relate to what you do, but they find it difficult, and they say, so has anyone ever seen a photon? And Greg very, very quickly responded, no one has ever seen anything else, which is true. I would say the same thing with caustics. An image is a caustic. When you have a point source, your lens is focusing down that light into the ultimately generated caustic, ideally, which is just one point. That's the best possible, the most independent possible caustic is just one point. If you have aberrations, this will extend into something curved like this. So no one has ever seen really. If they see properly, they see nothing but caustics. Yeah. So does that explain this connection of caustics rays with wave fields? Other thing that I'm going to mention at this point, another family that I will talk about briefly is the bezel beam, which is also a solution that propagates without changing. And you have a similar interpretation with rays, which I will show. And because these solutions have this maximum that seems to propagate without changing its dimension. Of course, the maximum does not propagate. The maximum is not an entity. It's an interference pattern caused by the light coming from all directions. But people have proposed using this for drilling holes, for example, in material, long holes. Once you understand this, you know that this will only work if the material is transparent. Because if you want to draw, you have the material, you want to draw a long hole here. Well, to get here, the light has to get in from the sides. Because the caustic is going to be caused by rays that come from other directions. So, of course, you cannot drill a hole on an object.
I have one comment.
Yes?
So, the interference, when you say it's intrinsically a wave phenomenon. So you are again going back to waves.
Yes. Yeah. So at the end, to get the beam, you have to, as I use the term, just waveize arrays, and there are many ways to do it that are valid in some cases. Of course, here we have caustic, so we have that condition that there's one of the methods we mentioned that would not work. But yeah, to get the features, you need to waveize. Yes.
Yeah. So since you talk about drilling holes, so is there any theorem or something that says that though in principle this airy beams you need like infinite power, but the ratio of the power kind of accumulated around the caustic, the rest of the thing, how efficient can you get?
Yeah, and this is an example. For example, here you can see that the power that is contributing to the maximum here is only that power that is in those rays that are giving rise to that caustic there, which is only a small subset of all the rays. So,
but that might limit the efficiency of how well one can do it.
Yeah, exactly. So for example, there's other applications which is sending signals very far, and there has been proposals of using airy beams for that because they don't expand. I am very skeptical about that.
Because you need more and more support.
Yeah, because you have a source. The airy beam is going to be raised like this, the zero authority basically, and raised like this with rotational symmetry. So there's a straight caustic due to the 3D aspect here. So if you get to the detector here, well, this is too far. I would have to be here. By choosing this propagation airy beam, is this last rays that will be arriving there, not all the others. Isn't it better to just try to send all the rays there? Put a focus at the detector and have all the light get to your detector. I think, again, once you think in terms of rays, it's clear that's better. So it's easy to be seduced by this propagation invariance, but once you understand what's behind it, you see that there's some pitfalls. Okay. So just this is one of those things that I did just for fun some time ago with another Miguel Bandres, which is when people were working a lot on non-paraxial versions of airy beams, so beams that follow circular paths. And they're saying, well, you can get arbitrarily close to pi/2 bending. And I wanted to just to show that, well, you can do way more than that. And again, it's thinking of rays of these beams as caustics. So there's a technique that people that design solar collectors use, which is the string design method. It's a very clever thing. Suppose that I want, usually they think of this as a pipe that you want to heat or something, but here I'm going to think of it as the caustic that I want to produce. So I make a model of a cylinder of this shape, and I wrap it around with string, and then I tie my string to this ring, metallic ring that slides freely on this metallic bar. And I come and put my pencil here. There's paper behind this. I slide the pencil and I draw a curve like this. The curve would look different if I made the string longer or if I changed the shape of this caustic, but I can always do this. Turns out that this is the shape of a mirror that if I were to illuminate this from above with a collimated wave, would create this caustic. So, well, it's backwards, but it's the same thing. So here I show the rays coming. I apodize them so that I got a caustic that is as uniform as possible. And of course, I made my mirror bigger. I could close more and more of the caustic. So there's I can come arbitrarily close to a full circle. And that's in 2D. If you go to 3D, it's even easier because before 3D, just for fun, what happens if you send an ultra short pulse to this mirror? you get a solution that looks like this. Little pulse that seems to be running around in circles. And if you time your pulse train right, it would look like it's going around and around and around. That seems to be violating physics as well, because you say, well, the centroid of this should go on a straight line at constant speed. And it is, if you calculate it carefully. Maxima, so the big lesson for students, maxima of intensity are not physical entities. They can do whatever they want. So even things like group velocity, take them with a grain of salt. So here you can create this type of thing that just goes around and around. So in 3D, you can do the same thing.
Spatial extent of that pulse
Yeah.
was larger, at least as big as the mirror, right?
No, it's much smaller. So the of the circle?
No, the pulse that was the
Yeah. That's right. Another way to do a full circle easily is to think in 3D. So I use a 3D version of this string method, and I can create a mirror that, when I illuminate from this point of view, creates this caustic that is transverse, let's say. And later I will mention that if I deform this mirror in some other way, I can create a caustic that is helical. Yeah.
How long can this helix be?
With this prescription, 1 cycle, just because of shadowing. If you made your mirror semi-transparent, maybe you can keep going or something. What is this good for? I don't know, but I had fun. Well, the intention was to show that some of the limitations that people had in mind are not there. So let me now come to the bezel beams that I was talking about. So the bezel beams, from the wave point of view, is a separable solution of the wave equation in cylindrical coordinates. So as they propagate, they look the same. This is a zero-Thorey bezel beam. It's very intense at the center. It's hard to see here, but there's a ring here and another ring. So it's, again, very tempting to say this is a beam. This maximum is a thing that propagates like this. Turns out that the energy, the power on each ring is the same. And much of the power on these rings is what will give rise later to the maximum here. There are versions with orbital angular momentum. So that was the bezel 0. This is the bezel 1, bezel 2, etc. And what I'm drawing here in red is the caustic. This is for the ray picture, this is the cross-section of the caustic for these beams. And I think I mentioned this yesterday, I'm not sure. The caustic is never at the maximum of intensity. It happens to be at the inflection point of the intensity. So here it's going from 0 like this and then like this. This has to do with that equation that I wrote here, where there was an extra term from the diagonal equation that tells you the spacing between wavefronts is different in regions of concave or convex curvature. At the caustic, because rays are there, the distance between wavefronts is lambda, so then you need it to be 0, and that's why the caustic has to be there. So what is the ray picture for this? So this is the caustic, and because now I'm explicit in 3D, I have to think of a 2-parameter family of rays. So I need 2 parameters that label each of the rays. And there are some other parameters that select the beam. So for selecting the beam, I can talk about the angle of the rays and the radius of the caustic. But once I fix that, the rays that compose this beam are all the rays that touch the caustic at a given angle with respect to the axis. So that can happen at different angles around the cylinder, or at different values of z around there. And the ones that are going to give rise to the caustic here, as you can see, were further away from the caustic at the beginning. Why are bezel beams quantized? Why do we only have, why cannot specify this radius, this angle and this radius freely? Well, here we have to waveize a little bit, so I'm going to draw faces along my rays. And as I move this around the cylinder, that face has to advance so that the face, yeah.
What do you mean by phase of a ray?
Suppose that I think of this ray as the optical path length. Optical path length divided by lambda. So I call that a phase. So that's periodic. And because these rays locally at some point have to be normal to wavefronts, etc., as I move to the neighboring ray, this phase has to move a little bit so that the closest point between two rays, the two rays have to have the same color, the same phase. So as I move around, that phase advances, and I come back, and this has to be consistent with this. And by chance, I almost hit it in this case, but that would only happen for certain radii for a given angle, or for certain angles for a given radius. And that is why we have only a discrete set of airy beams for any given angle.
You mean the ring-like structure?
Yeah,
It
the
is
ring
not
line, yeah.
continuous,
So I have bezel being 0, 1, 2, 3. So if I fix this angle, then there's only magic radii for which that condition would be met.
Yeah.
And that's what we saw in the previous simulation. But again, once you understand this, you realize that there's nothing special about a circular caustic. You can do the same thing with some other caustic. So I again choose an angle, and I can think of all the rays that touch that caustic at different points and different directions, and build a beam around that. And there are mathematical ways to state that, but with collaborators in Munster, they did the experiment. We wrote things, and so you can figure out ways to write a field whose intensity pattern is something that you want with some restrictions, and have it be propagation invariant. Propagation invariant is fine, not diffraction free, for some distance. So the Cornelia Den's student that did this was Alessandro Zanotti, AZ, and I think that's why he chose AZ. And AZ propagates nicely. So again, thinking about rays, it makes it very easy to see how to tailor the structure of light. So now I'm going to talk about the structure of Gaussian beams. Yeah, is there a, yeah?
Yeah, so since, how sensitive are these caustics to like long distance perturbations? It seems like you're building the entire network to form the acoustic.
Yeah, so these long distances of propagation are about this much, of course, in the lab. So you can think about this way. So if I want this distance of propagation and I want some angle of propagation, well, to get to the last point, I have to start from here, and I have to be able to precisely specify the phase of things here. The longer it is, the more that a tiny little error will cause a disruption. So you have to, there will be factors like this. Of course, there's turbulence, goodbye caustic, or goodbye the caustic that you want. But with this ray picker, there's an easy way to estimate precisely that precision that you need.
No, but I'm talking of like, can these caustics, for example, be used as like radar sensors? Like a form of very sensitive caustic here and something lies out there on this caustic instead. Because you kind of need this entire network in the ray picture.
Yeah. Yeah, that's a very good question, and that relates to something we were discussing today. When you design something, if it is very robust, you say great, it's robust. If it is very not robust, you say great, it's a great sensor. So it would depend on the situation, but I think, I mean, you could design your field to make it as sensitive as possible to whatever you want it to be. That's a very good idea. Okay, so now I'm going to talk about these beams, the Gaussians and their families, and which in a way are the least surprising physically, but they're the more interesting ones, I think. And I hope to convince you for several reasons. So these are modes of optical cavities, and the paraxial wave equation for these cavities turns out to be, you can find solutions that are separable in Cartesian coordinates, and that's what we call the Hermite Gaussians. So here I show one that is very high order. In polar coordinates, which is the Laguerre Gaussians, here I'm cheating a bit. This is not a pure Laguerre Gaussian. It's a superposition of two Laguerre Gaussians with opposite handedness. I just wanted to show the azimuthal structure. Normally, this looks uniform, but the face goes around. And there's a third family that is not so old, the Innes Gaussians, which is separable in elliptical coordinates. And I'm showing these lines here, these orange and blue lines. I will show you that these are the caustics for these beams. So these beams propagate without changing their shape. They just get bigger and slightly fainter as they propagate. So just in case you're not familiar with Hermite Laguerre Gaussians, this is the field distributions, amplitude and phase. So you have two indices. One is the total order, and one is an index that tells you how asymmetric they are here. Or in this case, for the Laguerre Gaussians, one index tells you how many radial rings there are, and the other one how many times the phase goes around. Although here we're not using the index P, we're using the total and the angular momentum. That's a technical detail. Okay, now I'm going to change channels for a second. I will not talk about polarization for the rest of the talk, but I want to get inspiration from polarization. So polarization, as you know, the electric field at a given point for a monochromatic beam traces an ellipse in time. And that ellipse can have different orientation of the major axis, and different ellipticity. And in fact, it can be round, it can be linear, or it can be round going in the opposite direction. So with the color I'm showing, if it is rotating like this, rotating like this. I'll be using this slide on my talk next week as well. So notice that to characterize orientation, we only need to go from 0 to pi, because that's already the same ellipse. So I have a periodicity of pi, but because I love periodicity of 2 pi, I use an angle phi divided by 2. So that phi goes from 0 to 2 pi. Similarly, to define ellipticity, I can box this ellipse in this rectangle. Turns out that the distance to the corner is the square root of the intensity, and this angle here is a good measure of the ellipticity. And again, that goes from the other one. For a circle, this is pi over 4, but because I also choose to put a half there, it's pi over 2. And then for linear is 0, and for the opposite handedness is minus pi over 2. So minus pi over 2 to pi over 2, that reminds me of latitude. And 0 to 2 pi reminds me of longitude. So I can represent pictorically this polarization as a point on an abstract sphere, and which is the Poincare sphere. So the north and south pole correspond to the two circulars. The equator corresponds to all the linear polarizations. The northern hemisphere is things that have a right-handedness, and the southern hemisphere is things that have a left-handedness. And all the elliptic polarizations live on the rest of the equation. So this is more than just a mapping of parameters. The Poincare sphere has a lot of properties. I'm going to mention one or two here. These are the polar coordinates. The Cartesian coordinates are the Stokes parameters that you can measure in the lab very easily. If you go through a birefringent medium, all you do is rotate the sphere. So there's a natural connection of the geometry of the thing with simple transformations. So a birefringent material just causes a rotation of the point over the sphere. And a related property is what we call the geometric phase. And again, you had Michael Berry here, I understand, very recently. So his name is associated strongly with this phenomenon. His and Pancharatnam's, of course. So I'm going to show the simplest example of geometric phase. Suppose that you have a right-handed circular polarization hitting a halfway plate. Yes?
So without in Poincare sphere.
Sorry?
I have doubt in Poincare sphere.
Yeah.
So I know about the block sphere in quantum qubits. So is it?
It is the same. So, well, it is the same and not. Yeah, I would say it is, in some ways it is the same. If you have your two electric field components of the electric field, the two meaningful ones, and you break them in the basis of circular polarizations, the Poincare sphere is the block sphere. It's the same thing. Poincare proposed it before Bloch, but it was independent. However, here I'm going to be stressing more than the mathematical definition, the geometrical definition, the association of the point on the sphere to a shape of an ellipse. And that's something that is not so much done in the Bloch thing. And that's going to be my main emphasis here. So, and I'm going to talk about things where the Bloch sphere per se is not valid, but the Poincare sphere can be extended. So it is the same thing, but with some slight differences. So here, if I have right circular polarization, I'm in the North Pole. I mentioned wave retarders cause a rotation of the point of Poincare sphere around the axis that corresponds to the polarization, the fast polarization of the axis. So that would be this one here. So and the angle of rotation is the retardance. So if I have a halfway plate, the transformation would be take me from here along this path to the South Pole. So you go from right circular to left circular. If I have a second halfway plate, I should have drawn the X here, that can bring me back to the origin. But if I rotate this second halfway plate, to come back to the original position, the axis around which I go changes. And that reflects the fact that if I look at how these reflections of the change of hardness happens, the phase of the final field will change. So changing this orientation of second element does not change the polarization, it just changes the phase. And this is one very simple example of a geometric phase. And that phase happens to be 1/2 of the solid angle enclosed here. I will be talking more about geometric phases on next week. So now that we saw that, let's forget about polarization. And first I want to mention that Miles Padgett and Johannes Curtiel realized that there's a nice analogy, and this connects to your question, between the Poincare sphere and a description for the lowest order Hermite and Laguerre Gaussian modes. Circular polarization sort of reminds you of a Laguerre Gaussian mode that goes one way, and the other circular to the one that goes the other way. Linear polarization with a well-defined direction reminds me of Hermite Gaussian with two blobs with a given orientation. And in fact, if I construct now, in the Bloch sense, a superposition of two opposite Laguerre Gauss beams of order 1, what you see is that by using Bloch's construction, you can assign a family of beams, I can show the face here, to any superposition with any amplitude and phase following the Bloch representation. So things with two lobes are Hermite Gaussians, they're like linear polarizations, and they can have different orientations. So that was, to my knowledge, the first connection between this Poincare idea and the structure of a beam. Then this was generalized in many papers to higher order beams, so they found that there are spheres for higher order beams. This will not be now a Bloch sphere, because the stage for this and this are not a basis for forming all the rest. This beam here is not a linear superposition of these two. It's something a bit more complicated. But the construction exists. You can generalize it, and there's a lot of work about these beams with Mark Dennis and my former student and postdoc Rodrigo. We propose a way to generalize these beams, this family of beams that include the Hermite and the Laguerre as special cases, which are called Hermite-Laguerre-Gauss modes. You can also represent them in terms of a Jones vector. So to make further analogies with polarization, there's a complex vector that fully represents these beams.
So these are like spin coherent states?
Yeah, it's exactly that. So and that's the other beautiful thing about these beams. It's completely analogous to a 2D harmonic oscillator and the whole plethora of physical systems that are described by that, like classical and quantum polarization and many others. So there's a and your comment came right at the right point. There's Majorana's prescription for defining higher order spin systems that can be imported into this context. And the better description then is not one that uses 1 point, but uses n points, where n is n plus 1 points. Is it? Where n is the total order of the beam. And then, so you have something that is called the Majorana constellation, the set of points that determines this. And there's a beam with some funny shape that it propagates. It would not change its shape. And it has a lot of degrees of freedom that are well reflected by all the coordinates of these points. Here we show the points as the corners of solids because it's easier to visualize. But the solid is not important. What is important is the points. Turns out also that just like for polarization, a birefringent medium rotates the sphere. The same thing exists for beams. The equivalent of birefringence is an appropriate combination of cylindrical lenses that thus has the effect of taking the spheres and rotating them around. So there's some inherent symmetries hidden in here in this abstract representation of the beam, what the beam is going to do when you use astigmatic systems with cylindrical lenses. Just also to mention how does this reduce to the Hermite-Laguerre Gaussian beams that I showed in the previous slide, where only 1 point is enough? Well, is where either all these points coincide at a point, or they're distributed between a point, which has most of the stars, and its antipode that has the rest. In that case, only one coordinate is enough, and you can get away with just 1 point. So that's why these other beams here are very specific. And this is the more general thing, where we have all these extra degrees of freedom. So we're, yes?
Yeah, so the last one kind of looks like a Penrose diagram.
Yeah, it does.
So here the caustics will be very complex.
Caustics are, so one of the things that motivated us to do this, and particularly this one here, which is what we call the Platonic beams, which are where you choose these stars to be the corners of perfect solids, so it's only a handful of them, is that in a way they are the beams of this type that are the least amenable to array treatment. So there is, the concept of caustic is the furthest from being useful here. And yet we showed that you can give some sort of ray treatment, which is related to what we'll be discussing. So rays can still tell you something, but it's not, caustics are not so easy to implement. And the reason is because the points are evenly distributed in the sphere. So one analog of this is in quantum polarization. There's the work of Luis Sanchez Soto, who we've discussed with a lot, and we're working on something together. He called this the equivalence of this the king states. Apparently, that was a suggestion by Penrose that they are the least classical polarization states. So, and least classical is the same as least Ray-like. But even if they're the least Ray-like, rays can, or classical picture can still give you some insights. So, and it turns out that the rays, so here I'm showing two types of points. So some are the constellation, the other ones are the corners of the the dual solid. Those tend to connect more with this ray-like behavior. But I will not have much time to discuss that. But one thing that is interesting is what happens to these beams when you use these cylindrical transformations. So for example, this with this constellation, because if I look at this sphere from above, I have 4-fold symmetry. That translates into 8-fold symmetry of the beam. But if I do rotations with cylindrical lenses, I transform the beam. I can look at this from different points of view, have different things. And when I look at this, I have 12-fold symmetry now. So you can, it's the same beam in some abstract way, but it has different types of symmetries depending on how we look at it in this abstract space.
No, go ahead.
Yeah.
No, I mean, usually for the Poincaré perspective, one always associates sort of the block thing, it's a two-dimensional. But suddenly the dimensionality is a lot more because
Yeah, exactly. Because you have a lot of points on the sphere.
Yeah, and I mean, so are there some? I mean, is there a better way to look at it? I mean, is there another perspective to it in terms of dimensionality? You are still looking at points on the surface, but yet you are associating literally infinite dimension.
Yeah. So the other way, and it's the same number of degrees of freedom, maybe up to a global phase, is well, these beams, the Hermite or the Daguerre of the same order, of the same total order as this, are a complete basis for that order. And the number of degrees of freedom in this constellation is the same as the number of coefficients that you would need in the expansion of the beam in terms of that basis. Either the same or half because there's amplitude and phase. But it's the same number of degrees of freedom when you think of it in terms of an expansion, in terms of a basis, or in terms of points. So the other one is thinking of the coefficients of the expansion. Well, that's easier if you want to create them because that's something you can feed your SLM or something. But when you want to think about the symmetries that this would have under some transformations, this is. And as usual, the best is to know both.
It's still SU2.
It's the, yeah.
So this is just kind of just experimentally if I think of actually creating these beams, as you showed that it survives over a certain time.
Yeah.
So the region where it comes out of, since you're like very, you're calling it like platonic solids and so on. So do you actually see a phase transition or anything? Like do you see?
No, actually, these as they propagate, if you just let them propagate, they stay the same. They stay the same.
Also, you don't like it's always the solid
Yeah.
phase.
Yeah.
You don't see it coming out.
Yeah, exactly. So they're constructed precisely to preserve their shape. You would see these transformations by using cylindrical lenses. So you have to enact a transformation.
So for this Majorana beam in this platonic solids, these will form a family of, maybe that's connected to the other question. Do they form at a complete basis?
No. So for each order, there's only one. Well, in fact, of the lowest order for each platonic solid, there's only one. So there's only 5 of these beams, and for 5 specific total orders. You can do degenerate versions where you put 2 stars on each point or things like this, but they're not a complete basis by any means. They're very specific cases.
But they are like propagation invariant as well.
They are propagation. Yeah. That's the thing that was inbuilt. And propagation invariant, because of the SU2 connection, the mathematical analogy with other systems, means their modes, their eigenstates of the 2D isotropic harmonic oscillator. You can map free space propagation to a 2D harmonic oscillator. Okay, so now I'm gonna come back to more the more standard beams, or beams that are not these isolated stars so much, but I'm gonna explain how I think about these in terms of rays, and in particular Hermite and Laguerre Gaussian system. And this is personally my favorite part of thinking about this. So I guess before I show you the figure, imagine that I want to think of rays now, and I want a family of rays, a set of rays that as it propagates, it keeps its transverse profile. The rays are straight lines, they cannot bend, and this transverse profile stays the same, just gets slightly bigger, following a hyperbolic rule. What family of rays would do that? And it turns out that we'll have to add many of those. So maybe I'll show you the answer. Look at the figure here on the right. There's something called rule hyperboloid. So I have a family of rays like this, that all rays are straight, the cross-section is elliptical, and it remains elliptical, the same ellipse for all distance of propagation. It just gets bigger, and it follows precisely a hyperbolic expansion. Now, this ellipse can be in different orientations, and it can be more flat or more round. Could you think of an abstract geometrical way to describe an ellipse of any orientation and any ellipticity? The bunker is here. It's exactly the same, but not from the superposition block-like point of view, but from the geometrical representation of an ellipse. So if the ellipse is round, I'm in the north of the South Pole, and depends on the handedness of that rotation. If the ellipse is flat, I'm on the equator, and where in the equator depends on the orientation. And the handedness here corresponds to the handedness of the skewness of these rays. In fact, for this ellipse of rays, there's something in optics called the skew invariant, which is to do with the product of the angle to the closest point of approach of the ray. And these rays all have the same skew invariant. So they all have the same skewness. But they have a definite sense of rotation, and that tells us whether we're in the north pole or in the south. So suppose that we want to build a Laguerre Gaussian beam. How would we do that? We need a 2-parameter family of rays because we're in 3D. So this is just a 1 parameter. I need to mix many of these guys. So what is conserved in a Laguerre Gaussian mode? Angular momentum, which is skewness. So if I use all the ellipses with the same skewness, that should be it. So if I do this, all these ellipses are just rotated versions of each other, so they all have the same skewness. So I'm going to start accumulating them. This. And now I have a ray representation of something here that starts to remind me of Laguerre Gaussian. It's dark in the center, it's dark outside, and it's round, and it has angular momentum. I can change, and each one of those ellipses or rays corresponds to a point here that is at the same height on this point right here. The vertical coordinate here is orbital angular momentum of the rays. So we are in a state of definite orbital angular momentum. I can change the radius of that ellipse, and I make this beam thicker or thinner. And that's like changing the P parameter of the Laguerre Gaussian. Notice that as opposed to the airy beams and the Bessel beams, whose families of rays are open, they're infinite, these ones are compact. They're all within some region, and the 2 parameters are periodic. It's 1 parameter that walks me around each ellipse, and another one that walks me around this curve. Now, the more interesting part, I think, comes about here. What does this sphere help you to see? If I have this circle or the one here, I have identical Gaussian beams, for example. They just have opposite handedness, but their shape is the same. So let me think about the shadow, the projection of this curve onto the equator here. So that's this black circle here. I will explain all this other messy stuff here. This on this side is a cross section of the beam. So here is all the ellipses of rays identified by color, so I can tell which one's which, and I can see clearly the caustic, the outer caustic, and the inner caustic.
So in the outer sphere, like how would I think of these two caustics that are?
That's exactly what I'm going to show now, which I think is a bit of geometrical magic. Its nature is I don't know why this is, but it's amazing that this geometrical property is.
I just have a question.
Yeah.
See, that particular latitude represents one definite OM.
Yeah.
Yeah. But if it is exactly at the pole, so what will be the OM state there?
So it turns out that when you waveize these, and I'll discuss that when you turn this into waves, you have something similar to what we had with the bezel beams. When I go around here and I come back, some phase has to match. And that tells you essentially that the solid angle enclosed by this loop has to be a half integer multiple of some basic quantity that is something like 2 pi divided by the total order. So there has to be an odd multiple. And that quantizes the rings that we can find. So it's not all rings that are already that are possible, only specific ones. And that's why we have quantization on the radial orders of the beam. And because it's half integers, 0 is not allowed. It's the smallest possible ring that is allowed. Okay. Should accelerate. So here's the thing that I think is quite remarkable. So suppose that I use not that beam, but some other beam with some more deformed path on the sphere that gives me on projection this path here. And I'm gonna define something that is called the medial axis, something that people in image processing and things use. It's a geometric construction. Consider this point of the Poincare sphere, of the path. And I'm going to look for a little circle that touches that point, touches the curve at that point, without crossing it, just is tangent to it, and it's also tangent to the edge of the equator. Its center is here. Turns out that there's another circle that does that. It's a bigger one. It's in this case containing the circle, the path, and its center is here. And now, as I move along the path, these two are gonna trace some curves. And they can do some funny patterns here. So we have a blue one here for the blue circles, and an orange one for the bigger circles. Now, this is the remarkable thing. Now think that this circle, this unit circle, is a chunk of the complex plane, real, imaginary. I can do a conformal transformation. I can say, so I put a grid here, and I take the square root of that complex number, and I look at its real imaginary parts. Essentially what it's doing is mapping any point here, so for example, 1, 2, 3, so let me look at this feature. 1, 2, 3, 4, 1, 2. Did I start from the right origin? No, I think I started this. And I can, this grid is gonna get the form. So I have 1, 2, 3, 1, 2, 3, 4, or 5. I didn't count correctly. And I map these two curves, these two medial axes. They are the caustics. They are the caustics of. So the path on the Poincare sphere is encoding somehow the brightest parts of the beam. The structure of the beam is hidden in this curve. And this lets us see that these two set of caustics are not independent. Because if I know this caustic, for example, I could map it back here. I can say, okay, I drag these circles here. I see what curve they are tangent to. Then I find the other medial axis, and I map it back. And that would give me the other caustic. So they're interrelated. They're not independent. So the inherent structure of the beam is hidden in this Poincare sphere. And it's something that the wave picture would not tell you. So that's, again, rays give you extra intuition that you would not get from waves. So what I have here, this red, this blue, and orange curves are precisely those two medial axes, which in this case are quite trivial. It's just circles themselves. I map them. They're circles. Those are the caustics. Let's make this more fun. What happens if I make this Laguerre Gaussian beam go through cylindrical lenses? The sphere would rotate. So if I rotate the sphere, yeah, this is the slider. If I rotate the sphere, now this is tilted. The path is not a circle anymore, it's an ellipse, off-center ellipse. The medial axis start getting funny shapes. It's going to look more like a fish. But if I map it, I get the caustics of the beam. I can keep rotating until this is perfectly vertical. And Mathematica doesn't like perfectly vertical for some reason. But that's all right. This beam is now square. The shadow of this is a straight line. The medial axis you can find are parabolas, whose focus is the origin, and if you map that, they turn into straight lines. It turns into a rectangle. How do we call this beam?
Edgy.
It's a Hermite Gaussian. And we have the same quantization of the solid angle, etc., and that gives us the quantization of the Hermite Gaussian. So I can change that radius, and it will give me something that is more square or more flat. Is that clear? Okay. So this explains many things. So I talked about geometric phase. Turns out that you can do geometric phase with beam structure, and I think Kiko Galios did the first experiment with the lowest order Laguerre Gaussian, Hermite Gaussian beams. And for example, if I have this path, I'm going to use the Hermite Laguerre Gauss representation of representing all this ring by a point. So in that old representation, we represented this beam by just one point here, but here we can see that with the rays, it's really a circle centered at that point. So this is telling us more about the structure of it. Now I'm going to send it through a cylindrical lens. Yes?
So the distance between the two caustics
Yeah.
is set by the solid angle?
It's determined by the solid angle. Yeah, exactly. So suppose that we transform this into a Hermite Gaussian beam, but I keep going, and I can use cylindrical lenses to change the OIM of the beam. And then I use an identical setup to come back, but I rotate my setup so I come back a different way. This beam looks exactly the same as the first, but let me show you. So from here to here, it's the same shape, it's the same handedness, because if you go green, aqua, blue, etc., it's going to be the same thing here. Green, aqua, blue, etc. But can you tell me something? What is the difference?
The phase change of time.
The phase, which in the ray point of view is not the phase, it's where each ray is. So we can think of this as we have a folk dance group, a lot of dancers, and they do their dance, they start in some formation, they do their dance, and they come back at the end of the act to the same formation. But Joe started here and he ended up there. the dynamic phase is the optical path length of each ray, but each ray started with a different phase because of they correspond to different points on the wavefront, and at the end they ended up a different place. So because someone with a different phase is now where the first one was, the total field is going to have a different phase. And that's the geometric phase. It's really geometric. It has a ray optical interpretation. It's not the same ray. It's a ray that started with a different phase. Yes?
In the last lecture, you told about how the ray bends and it changes its there's a beam and multiple rays they bend and again they form a similar the similar structure like they had before. So just the rays they dispose in the point in space. Is it the same thing?
Yeah, it is the same thing, and it's the same thing with the area beam. The area beam or the vessel beam, if you look at the ray distribution, later it is the same, but if you look which ray is where, that changes. They're cycling their roles. And that creates these extra phases.
So if you don't have a way to index the rays, so we cannot tell the difference.
Exactly. I'm very happy you said that because in 2 slides I'll show that you have a way to index the rays. So this explains the geometric phase and explains this QuIC phase, the fact that at the wave beam the phase advances at a different rate. So this one is because this geometric phase because we cycle the ellipses, but the QuIC phase is without any lenses. We just let the beam propagate. So it's a cross section, and I'm going to propagate at a constant speed. Focus on one ray. As I move, that ray is going to be moving on a straight line. All rays are moving on straight lines. But the global pattern stays the same, and the rays that were contributing to some part of the feature are now somewhere else. So again, you're cycling the rays. The initial rays had different phases. So the QuIC phase is this cycling within an ellipse of the rays. And if you calculate it with geometrical optics, you get exactly the right geometric phase, the right QuIC phase. This also lets you see
so
that.
Is the dynamic phase acquired by one particular ray in moving from?
Yeah. So there we can say there are three different phases. The dynamic phase is just accumulation of optical path length. The QuIC phase is cycling of the rays within an ellipse. And this geometric phase, when you have lenses, is cycling of the ellipses of rays. This also shows you that, like area and vessel, we're not so used to this, but these beams also have self-healing. If I block some rays here, and I let this propagate, new rays are going to replace those rays at that spot. Of course, this is a self-healing that my hand will heal, but my other hand will start to hurt. The problem is just migrating somewhere else. For those beams, because we have an infinite reservoir of rays we don't care about, that problem is going to that reservoir, and we pretend that everything heals. But you cannot get full healing. The problem just migrates somewhere else. And in fact, with a colleague in Rochester, we precisely use what you said. We can label the rays. We can measure this geometric phase by blocking part of the beam, seeing where the shadow goes. So if I block part of the beam and let it propagate, here we block quite a bit of the beam because it was better for measurements, but I could have blocked just a little part, and that shadow would migrate somewhere else. And with that, we can, just looking at the center of intensity, you can measure the geometric phase without any interferometry. It's just a geometrical transformation. So this shadow is essentially what you were saying, is labeling the rays. And yeah, compared to interferometry, you get exactly the same phases. You have to. So this is I like to think of the analog of this is the dance troupe that I was mentioning before, where they do their dance. Well, one day, especially now that I live in France, there was a strike of the bus service, and a lot of dancers didn't arrive to the rehearsal. So this one started here, and they did their dance, and they ended up somewhere else. So now it doesn't look the same, but you can tell from there where they moved. Okay, I think I'm gonna wrap up this quickly. So this is just, it turns out that for the Hermite-Laguerre Gaussian beams, for all these beams, if we use the ray dressing approach with Gaussians that I discussed on Tuesday, and you use the right gamma, the integrals come in closed form. And it's a very nice derivation that, it's one that we found, and then we found that someone else had done a similar thing, but well, that's okay. But when I teach math methods, for example, I always teach contour integration and residue theory. This uses residue theory. So there's at least one application for residue theory. And what you get is what I was saying before, is the contribution, the coherent state, going to your analogy, is the contribution, the wave contribution to one ellipse of rays. And it turns out to be a Hermite Gaussian evaluated at a complex argument, where this coordinate variable is dotted with something like a Jones vector. So if that Jones vector is circular, you get a Laguerre-Gauss. If it is linear, you get a Hermite-Gauss. So what these coherent states look like is they mimic the shape of the ellipse. That's the intensity, and that's the real part.
So n is the order.
N is the order. And n corresponds to how many times the phase goes around here. So yeah, I have that variable here. So if I make this 10, yeah. So this gives exactly closed forms actually for the Hermite-Laguerre-Gauss and all the Hermite-Laguerre-Gauss family. So the rays contain all the information about the waves. You can get the wave fields from the rays. But you can also have fun and design other curves with other beams. We have different caustics and different shapes. And I think I'm running out of time. The third family of beams, the in-Gauss beams, they're the most fun of all. There's some very nice geometry behind them, so maybe I can discuss this on Friday before the other topic. But we're talking about analogies. They have analogies with quantum systems. There's a model that I didn't know about, but many of you will know, the Bosse-Hubbard-Dimer model for condensed matter systems. Turns out there's many beautiful analogies between these beams and that system. So, and behind that, there's a lot of nice geometry. So maybe I will, before going to the last topic, I will start next time with this. So, and also discussing how, from that description, Airy, Bessel, and others beams fit within this framework as limiting cases. Maybe just to finish, I will come back to this as accelerating beams, but which is what you asked. How do they look in 3D? So they would look something like this. So they have a caustic that is like this, like a corner, and that bends. But there are other variants that have other shapes like this.
These are not spherically symmetric, they're circularly symmetric.
No, these are the paraxial ones. So they're parabolic. So let me see. But by doing a similar analysis, you can find that there's a variety of shapes of acoustics, and there's a similar fundamental geometry. The two caustics are not independent. There's a curve that tells you the shape of the caustic. It's like the Poincare path. And this is a baseline, and all the circles that touch the two, their centers trace the caustic. So this is for a standard airy beam. You can tilt it. So there are tilted airy beams where each bend at different speeds in the two different directions, or you can even deform it. But the two caustics would not be identical, but they would satisfy these geometric restrictions. And what happens when they go non-paraxial? And I'll try to do this very quickly. So if I want to go circular, I discussed the mirror solutions before. So for example, this one, if I now go and look in at that, it turns out that something similar happens, but the caustics bend. At some point, I came up with a geometric interpretation, and I confess I forget the details, but it's all in this diagram. You can describe. There's some geometric rules hidden here in these curves and these circles that tell you what is the shape, the allowed shapes for these curves here. So there is some fundamental geometrical symmetry hidden in the shape of the caustics. So just to finish, one last thing that I want to show is, so I talk about this mirror and this other mirror here that does the helical. Turns out that when you go from something that is not helical, something that's circular, to something helical, this caustic, which is degenerate, these are rays, breaks the degeneracy. The caustic breaks into two sheets of caustics like this. And there's equations that determine that. So just to show you the detail of the caustic, so this is a caustic for the round one, so it's something like this. But for the helical, if I come in and zoom, you can see that it's exactly two-sheeted. So there's a breaking of, it's like a splitting of levels, a breaking of degeneracy that opens the caustic like this. Okay, so with that, I finish. So again, I hope to convince you that rays, we shouldn't forget about rays just yet. They're quite useful. They tell us a lot about what a beam does and all the geometry that is hidden in there. And there are many analogies with polarization and things, and I think co-authors of different parts of this work, the theorist and the experimentalist, and I thank you for your attention.
Okay, so we had a lot of questions, so we have more questions. Take it.
So firstly, like, how do you get this geometry construction? It's not magic. What is the intuition behind?
So it all started with discussions with Mark, who's a good friend. He was a student of Michael Berry, and I visited him several times when he was in Bristol. And he told me about this problem. He wanted to understand his Gaussians, and we started thinking about these ellipses of rays. And just scratching things, we started seeing all these nice geometrical patterns come out. He had thought about this Poincare sphere for the rays, for the one family of rays. Then we started putting things together, and this relation between the caustics just came out.
But something, like when you're constructing this thing, something seems to be remaining constant, or the length of the string when you're actually
Yeah.
or like these two spheres.
Yeah.
So it's like something in this 2D geometrical structure seems to be remaining constant, which gives you the right constant.
Yeah, and
How to think of that?
so with the string, I think it's Fermat's theory, for example, Fermat's theory. When you focus light, so to have two rays that interfere at one point here, they have, at the point across, they have to have the same optical path. So if I start from a constant, I'll use this line that I have here, constant wavefront, which is my metallic bar, and I come here, and then to the pencil, and then to this will ensure that the optical path length is consistent for the two rays. So fixing the length of the string in that case is essentially Fermat's theory.
To construct a parabola, we require, for example.
Yeah, we could do exactly. So if I wanted to create something, I just put a parabola. Yeah, we could use the same construction. So in fact, there were people that were there are many beams with names nowadays, and there's one that is a non-paraxial one where this is a hyperboloid one, which has some nice ones. But it would do it with the same.
So, will you give us a L-dependent caustic?
L-dependent caustic.
I want to separate out L beams, for example. L-dependent spatially varying caustic is possible. Can you construct? Maybe you can. That's what.
So I guess there are many possible ways to answer this. So one would be, if I come to this slide. And I tilt something like this. I can think of the caustic. So each point on the caustic maps to some points here. And those points I associate with a point here. And that point I say to something here that goes to some rays here. And because they have a different height on the sphere, I can associate locally the equivalent of an L, which is not, in this case, discretized. I can associate a local angular momentum with the caustic. And I guess what I would be is the rays that are touching the caustic locally, they have a skewness. And that skewness is yeah. So if I call this height some normalized version of L, then I could map L to different points, different values of L to different points
So
of
this
the
is the
caustic.
context of L sorting, for example, which people do require.
Yeah. So that we really want to use the discrete version of things, which is where the ray has a bit more, ray picture has a bit more trouble. We can use what we can do is break the beam into Laguerre-Gauss modes, and then for each one of those, use the rays and see. So actually, it's interesting, and I don't know if this has been done or if it will be interesting, but there are those systems that Johannes and Martin Levery and other Miles Padgett have designed, and Bob had an enhanced version for unfolding the Laguerre-Gaussian beams. Just doing a ray tracing of these to see what the different modes do. So rather than doing the diffraction calculations, I mean, it's going to be the same thing in a way, but it'll be interesting to see what is the ray structure after that. If you just trace the rays through those surfaces.
Other question. These caustics is well explained through rays, waves also can be explained.
Sorry?
This caustic is explained through rays.
Yeah.
So these waves also can explain these caustics.
Yeah, in a way. It's more blurry. It is really a ray concept, but in simple, at least in simple paraxial beams, where the caustic is clean, there is no other rays are going through the caustic. So if I have, for example, this case, well, this can evolve into any shape. It doesn't have to be parabolic or circular. And I look for the wave solution, it will have the intensity is going to have some pattern like this. So this is the case exponentially because there's no ray there. This oscillates because there's two rays at each point that are sort of interfering. The caustic coincides with the inflection point of the amplitude. Almost with the inflection point of the amplitude. It's really the inflection point of the amplitude. So if you notice, here there's no inflection point, it's always the curvature is positive. And here, for the amplitude, because the amplitude is going to do something like this, the derivative is always looking towards the axis. While here is looking away from the axis. And the inflection point where that behavior changes coincides exactly with the caustic. Of course, if you have another part of the beam that is superposed, that messes up things. But this is a semi-wave, rigorous way of defining where the caustic is.
One more question.
Yes.
So means this ellipses on pointless sphere
Yeah.
maps on angular momentum beams. Means
They can, yeah.
So it's one more degree of freedom is there in apart from the angular momentum radial modes.
Yes.
So means how it does map on pointer.
Yeah, so that would correspond to the different radii. So different, if I change the height, oh, no, wait a minute. For a given height, there's another parameter that I haven't specified here, which is the total order of the beam. So that is, for each ellipse, if I just look at one ellipse, and I do the same game that I did for the bezel beam before, if I paint each one of these rays in colors, and I go around, and I see how many times the phase wrapped around each one of these ellipses, that -1 is the total order. And that's an extra parameter that is sort of a normalization of the sphere. Really, you should think of not of one sphere, but it's a bunch of nested spheres that are each for a different n. So once you have a circle here, if you specify that and the total order, then the radius of the circle, the allowed radii that you have for the circle, correspond to the p index of the Laguerre Gaussian beam. So for example, here, if I make this like this, this is a very thick beam, so it's high p. But if I go to the other limit here, this is a very thin beam, so it's p equals 0 or p equals 1.
Okay, any other questions?
Yeah, so in this, like, if you have like weak interaction between modes, weak interaction, like some weakly nonlinear system, how stable are these, or do you expect like kind of?
So nonlinearity or just inhomogeneity?
Not some interaction between modes.
Yeah.
There are all these excitements of this many-body localization and so on.
Yeah. So that's something that I've been curious about, and I have not pursued because always more than things. Is can this ray model help you with nonlinear propagation? There's a catch, which is, the advantage of ray optics is that it's much easier to trace rays than waves. But my fear is that to get the local nonlinearity, you need the wave. So you would have to trace the rays, turn it into waves, calculate the local refractive index so you know what to do next. So if there's an easy way to estimate the nonlinearity just from the rays without doing the heavy waveization, then I think there's something. But whenever you have caustics, for example, the intensity is going to change in such short scales that I think there's no option but to reconstruct the local field to know what the nonlinearity will be.
So self-phase modulation.
Yeah, exactly. Yeah, so that's one catch-up. Yeah. It's really useful for propagating just ray tracing and then turning into waves if the field has nothing to do with the medium superposition.
Okay, so again, excellent talk. So next talk is tomorrow, same time, same place, and it will be some leftover from here and partial coherence, right?
And partial coherence, yeah.
There are some tries still left. And with that, let's thank Miguel, and if somebody
Thank you
wants,
for your.
if you still have questions, feel free to be around. Miguel is here until May 2nd, so students or anybody wants to see him, you can write to me, and can. Okay.
No problem.
Yeah, I'll take it. Amazing.
Sorry, it was a bit long.
No, it's fantastic.